Hello everyone, this is Bradley. There were lots of Plexus animation that's either done natively in Blender or done procedurally with animation nodes. And the two advanced Plexus animation that I uploaded these days was due to a question people asked me on social media. So firstly, if you have a certain animation that you want to know how to do in Blender, regardless whether it's done by Houdini or Cinema 4D, I may be interested in knowing them. There are tons of things I'm not able to do, but at least it's free for you to ask me. You can do either by comments on YouTube video or find me on Facebook where the link is in the description. Secondly, originally I was not interested in making a tutorial for this very soon, but surprisingly there were multiple people who are interested in this animation, so I prioritized making this tutorial. Next time, if you would like to know how to make an animation that I uploaded, please let me know. So back to the original topic. As I said that people already made tutorials about Plexus, but there is a special request asking whether it's possible to get the polygons on Plexus, which turns out to be the topic today. A breakdown is attached in the pinned comment if you already know how to make a Plexus and wish to jump to where we are generating polygons. Otherwise, I'm going to start from the beginning of making infinitely loopable Plexus. So let's start. So the first thing that I'm going to do is to distribute the points within the spaces. And I'm going to use a method which is probably not mentioned in other person's tutorial and not even in my tutorial as well. So this is a new method that I would like to introduce to you. So firstly, in the node tree, I'm going to hit Control A and search for distributed matrices. This is probably the most efficient way if you are going to distribute a points in a 3D space, besides the particle system. And if we activate these, let's just turn up the Z. So now you can see we are distributing all the white markers within a cube. The issue, however, is what if your camera is going very far away, like just right now, if I'm looking at this entire thing, a cube is somehow ugly. And I want everything to be evenly distributed within a radius, which means a spherical. So how to do this is something I would like to introduce to you. Okay. So I'm going to generate a UV sphere and hope this to be kind of large. And let's take an integer input to synchronize XYZ. You don't necessarily do this, but it does not really matter. So let's take it 7. And I'm also going to use a float input. Remember to keep this cube a little bit larger than the sphere, or equal size, does not really matter. But the whole point is we need to have some axis of points, which is outside the sphere. Okay, next thing is we're going to use a node, which is called is that inside the volume. So is inside the volume, okay? And you can see there is a dark green BBH3 socket. So you just hit W and it goes to left and hit BBH3. And I'm going to select objects as the sphere. So I'm going to determine whether this vector is inside this spherical volume. And the BVH3 essentially is a algorithm that calculates the bounding box. So now if we hit W and it goes to viewer, you can see it generates a Boolean list, so it answers whether it's in volume or not. And we're going to use a node which is called a mask list. So, and it has a Boolean inputs. So basically now what I'm doing is if the vector is inside the volume, then it will be outputted. Otherwise it will not output. So initially we have about 343 points being generated by these distributed matrices. But now after the masking, we are only outputting 123. So this is the point. So we can also confirm the things with these 3D viewers. So now you can see the 3D point has been largely eliminated and so on. And you can definitely decrease its size so that more points be included on the edges, like kind of increasing the resolution and so on. So I think this is kind of very efficient way to do such kind of function. So next thing that I'm going to do is to vector math, because I want to add some randomness. Now it looks too uniform, so I'm going to add a vector wiggle. And I'm going to hit this button to create a list. And I'm going to put this list into the count. It will automatically generate a get list length. So I would basically, the idea is for each of these points, they will have a different wiggle vector added to them. And to change this value easily, I'm going to use a vector from value. So I'm going to use this one value to control x, y, z numbers. So by taking a look with this 3D viewer, you can see basically they have been randomized, and you can change this value, which is nice. And now we can hide this sphere. So even if you add some randomness, they definitely, some of them go beyond the sphere, but the general shape is still spherical. I think even if you add a lot of amplitude in the wiggle, it's still, general shape is still a sphere compared to having the cubes. So let's just take a look. If we just adding a cube, then you can see it's you can see it still looks kind of cube, and I think it's not what you want essentially. So this is good. Next thing is we're going to generate icosphere or UV sphere on each of these points. So let's take an object instance and object transform output. And I'm going to use the get length that we created earlier, goes into the instances. So basically we're creating same amount of wiggle vectors and also the same amount of instances. And for the instances, we're generating an icosphere, and I'm going to change the subdivision to 1. This is basically to save the power of my computer, because we are going to instances maybe about 100 times, I suppose. So I'm going to instance this icosphere. And for this the parent icosphere, I'm going to add a wireframe modifier, and I'm going to change the material offset to 1 and turn off the replace original. And in the material, I'm going to create two material. One is random color, and another material which is called wireframe. Okay. And I'm also going to generate a vertex color, but you don't necessarily to follow this step. It does not really matter in this particular tutorial. So then we're going to copy this for object and deep copy. In general, copy for object copies materials and the modifier and all other settings. Deep copy allows each icosphere to behave differently, something like that. So object goes to object socket, vector goes into vector. So now you can see everything has been exploded. We no longer need this icosphere, so I'm going to drop into a hidden composition. Okay, so now everything has been exploded, fine. We're going to turn on the scales and the rotation. So let's firstly deal with this scale. I'm going to take a random number and the vector from value, because I want to have uniform scales. So now all these icosphere has been shrinked equally, but I'm going to generate a random number for each of them. So get the list length goes into count, number going to values, and I'm going to decide what's the maximum and the minimum scales for them. So something like that should be enough. Okay, this is good. And for rotation, we're going to generate a Euler wiggle. I'm going to generate a list, and this get list length into count. I'm going to change the amplitude into 360 degrees, and the rotation, and the Euler into rotation. So now basically these are done. You can definitely organize the tree better. I think you get a kind of idea. Here's one thing that I hope you to realize is the reason I use these wiggle nodes compared to random series nodes like a random vector and random wiggle is that if you are changing the evolution, then all these icosphere will move. If you would like to do a looping animation, essentially what you would like to do is if the evolution goes to 1, and it should go back to 0, back and forth. So you can do this by sine wave, like a float mass, and get a sine wave, and put a time into that, or you can control the number by yourself. Just to remember that I think in sine wave, 2 pi is a cycle. So something like that. Okay. Or else, there's another way which has been used by Kress-Pregner and probably Ducky3D as well. So in this curve object, there's an advanced option which make a knot. I'm going to just use a Celtic torus knot plus. I think yeah, I think this is good enough. If you don't find this knot object, then I recommend you go to edit and search for curve extra spline, extra objects. Yeah, add curves, extra objects. Then you can find this object, or you can type any math function to generate your own knot. I'm not going to really discuss the knots at this moment, but you kind of getting an idea. And I'm having a camera. I'm going to use the constraint and follow this knot path. Okay. So now even if I'm hitting the follow path, it does not occur anything. It's because if initially you're, so firstly let's Alt G claim the location of this camera. Next thing is within this knot. For some reasons, if you already bevel this knot, then it won't read by the constraint. But later, if you recover that with the bevel, then the constraint will keep working. I don't know why. I think this is more or less a bug. Next thing, I would like to have this camera always facing at the center. So I'm just I created an NP in the center. It's just called the light target. So now this is done. And by hitting this fixed position from 0 to 1, it cycles. So this currently is it. So let's just keyframe that very quickly. I'm going to hit everything like 350 frames. And initially it should be 0. Next thing it should be 1. Okay. So now it goes at the end to 1. I'm going to use this cycle to control the evolution. So let's take a object matrix input and select our camera. I'm also going to take the object decompose matrix. Then we got the translation and the scale. So I'm going to put the translations into the evolution. So you can see I'm putting everything into evolution because the evolution is a single number, but the translation, I mean the transform contains x, y, z, so it just separates the vectors. I think this is understandable. And I'm going to put the same X into evolution, or you can choose Y or Z. It does not really matter. It's the same. They're cycling through. So basically, by doing so, the transform and the rotation is going back and forth. As you can see, their movements. So you're generating a looping animation in this particular case. So another proof is if we just go back to beginning, you can see they're not moving. Okay, if you are not satisfied with the rate of movement, then I would recommend just add a float math and times a number that you wish. So now I think they're moving kind of fast, slow, whatever stuff. So I think up to this moment, a basic concept of Plexus has been made. The only issue that we haven't done is to connect these points. So to do that, it's actually very simple. There's a node which is called find close points. So I'm going to put the points into that. So for each point that we generated through this math, it will look for 3 closest points and connect them with an edges. Now you cannot visualize these edges, but you can convert them to actual stuff. So one way to do is edge to cube. And you basically put the locations into points, edge into edge indices. Another way is splines from edges. Basically the same idea. The only difference is whether you are outputting a actual object like the icosphere or actual splines, which is a curve object. In this case, I'm satisfied with having a mesh. So let's just do mesh object output and act a target. So if you're unsatisfied with the resolution, just increase that so that more like kind of cylindrical, and turn down the radius. So now basically this has been done. You can also change the amount, so that's change the connection. So I think 2 is a very good number, because 3 you will have a lot of interconnection, which I mean essentially does not make a difference. And in this target, I'm simply going to add a material. Let's just call that edges. Yeah, should be enough. So now everything is moving as we've done earlier. Next thing is finally goes to the most initial questions, how to actually generate faces within this Plexus. So let's firstly hide the animation node and hide our target. And I'm going to create a plane. And it goes to edit mode, select one vertices, and I'm going to dissolve that. So now we have a triangle. In fact, in such kind of Plexus that you're generating plane, I think only the triangle is really applicable, because triangle is enough to define a plane in the space. But if you have 4 points, then it's just a very weird. So anyway, so the whole point is now I have 3 vertices of this triangle. If I ask each of these vertices goes to one location of this icosphere, then you just generate a faces within this Plexus. So how to do this exactly? Let's turn off this plane. No, let's turn on this plane. And let's generate an object instance. Also add a material of this plane. So let's just add a random color. And I'm going to take an integer input. Also for this random color, I need a vertex color. Yeah, so now this is good. So I'm going to put this, so I'm going to replicate this plane for 15 times and copy for object deep copy. Next thing is I'm going to select this node, hit W, and it goes to right, so loop through objects. In the parameter, I'm going to add a vector list. And I'm going to use the initial location for this entire whole thing. Yes. So what I'm doing here is this loop will be run 15 times. And each time I'm asking this loop to look for a point within this plexus, probably a random point. So let's get a random list element. I'm going to change the type into single and put the list into, and I'm going to put the index into seed. The index will change for each loop, and as this loop will be run 15 times, this index will go from 0 to 14. So basically, by changing the seed each time, we're looking for a different point within this plexus. Next thing is I'm going to take I think it's called find the nearest points node. So I'm going to look for 3 points in total. So element goes to x, y, z. So basically vector. And we need a KD tree. So KD tree in this particular case, it's just a pool of vectors. So again, you hit W and goes to left data input, and you just construct all these points together. So basically we are starting with the point we selected and asking it to look for 3 points total nearby. So now we have 3 points. And we're going to connect these 3 points, or actually use these 3 points as a guide for the plane to be regenerated. And in this case, we're going to combine mesh. And I'm going to put the vector into vertex location. I'm going to object mesh data to use the indices we have for this plane to regenerate new meshes. In this case, I'm going to hit U, goes in edge indices and the polygon indices, turn off the polygon center. So I'm going to use the edge indices and the polygon indices. And then we're going to mesh objects output. So here we're going to generate like 15 triangles. So just to put the objects into the socket. So instantaneously, you can see we have a lot of planes being generated. I don't know if it's actually 15. I think it might be less than that, but I'm kind of satisfied. If you think you get less triangles, you just increase the numbers. 45 may be too much. So anyway, just generates many points. And again, you have the seed. So you can change the node seeds. It's completely procedural. One thing I have to remind you is that you can take a float math, because the index is essentially fixed, but you can use a float math and connect that back to parameter, and I'm going to name that as a seed. And you can actually, no, let's redo that. So let's hit this plus and make an integer, and put the integer into the math for the seed. I'm gonna name that seed, and just take a large number, 15 or other things. So by changing the number, you just get a completely different random seed, which is essentially cool. I think after, oh, by the way, another thing is for this vector is also the same. You can change the seed for vectors or other things. So you can do whatever you want. It's completely procedural. So I think up to this moment, this is basically done. Let's turn on our targets. So you can see we have the animation. The only thing that I'm not satisfied is that this plane will disappear if the points change dramatically due to the movement. But I also think this is the nature in this Plexus system. So I don't think it's possible to really fix that very well. Or it's possible to fix that, but it will make life dramatically bad and so on. So anyway, so let's briefly talk about the texturing, because I think getting random color and color shifting are kind of critical in my animation. There are generally two ways to get such kind of effect. One is to use animation node and the other is not to use animation node. For the method that does not use animation node, I've made a tutorial talking about the random color, how to change the random color seeds, how to shift in the color and so on. So I highly recommend you go to right upper corner where the link has been provided. In terms of the method that use the animation node, so let's go to the shader. So in our random color, which has been used 220 times, I'm going to firstly shift that into emission shader. And I'm going to take a vertex color in which we generate at the beginning. So in our icosphere, so let's take the random color. We have the vertex color of name, which has a name of color. But in our plane that has been newly generated, actually it does not have a vertex color layer. So let's insert a vertex color layer. And let's name the same name as a call. Then we are going to generate random color. I think I'm not going to really talk about this specifically in this tutorial, because I would like to go into more details about how to build the presets of this random color loop. So by using these presets, I just need to input the seed. Then it will basically do everything for me. So let's just briefly change the numbers. And we're going to do the same thing with icosphere. So let's generate a loop. So now let's see what we actually look at. So now we get a random color. So let's just change the hue shifter. So the icosphere has a different color group compared to the plane. And then we're going to turn on the bloom. Also in shader. So let's go to the shader. I'm going to turn on the emission. And for these wires, I'm also going to change that to emission. Just emit white. And so on and so forth. Obviously there are many things that you can potentially do. But I think I'm not going to go more details beyond the topic. I think you get a kind of idea. Final thing that I would like to mention is for this torus, so now the origin is in the center, but you can try to just scoot it a little bit, so sometimes the camera move closer in the center of this plexus, or sometimes move beyond. And in this wireframe, let's just turn that to dark. You can also increase the thickness of the wireframe that I've mentioned many times by using this objects attribute output nodes. Like you just copy data path, put object ins, and use a float input. So now you can see the visible wireframes and so on. Let's also turn down this word. So you get a kind of idea. There are many things you can potentially do with that. I will probably stop here, and I hope you enjoyed this tutorial. I'll probably see you next time. Bye bye.